Welcome to the second lecture in our 11th module. And so this module is on linear regression. In the first lecture, I discussed the basics of linear regression. And now in this lecture, I'm going to talk about measures of variance and hypothesis testing for linear regression. Okay, so let's start out by talking about the total variance around the dependent variable. And remember, the dependent variable is referred to as y, and so here we're looking for the variation around the mean of y. So in the graph, the mean of y is that dotted horizontal line kind of that goes across the middle of the graph, and what we are looking for is the total variation around that line. So that's the total variance of each individual value of the dependent variable around that horizontal line, which is the mean of the dependent variable. This is also known as the total sum of squares, which you've seen earlier in the course, and it's calculated simply by subtracting the mean of y from each individual observation of y, squaring that result, and then summing it. And so that gives you the total sum of squares, which is the total variation in y. And so that can be divided, the total sum of squares, the total variation can be divided into two parts. One is the explained variation, two is the unexplained variation, or the error. So let's talk about the explained variation. And so this is the explained variance of the dependent variable y, which is also the variation of the regression line from the mean of y. So in the graphic there, the regression line is the red line that increases from the origin on an angle, and so that's the regression line, and then the mean is again the dotted horizontal line. And so the regression sum of squares, to get this, what we're doing is we're subtracting the mean of y from each individual predicted value along that red regression line that increases from the origin there. So each of those individual white circles on that red regression line, the distance from each of those to the mean of y. What we're doing is we're subtracting the mean of y from each of those, we're squaring the result and then summing it. This is referred to as the regression sum of squares, SSR. And this is the explained variation in y, explained by our regression model. And then secondly, there's the unexplained variance of the dependent variable. And this is the variation of actual values of y around our regression line, right? So in the actual cloud of data, you're going to have that regression line, and then you're going to have the actual values plotted here. They're shown in blue. And so the distance from each of those blue values to our red regression line there is the error. And so the error sum of squares, what we're doing is we're subtracting the predicted value of y from the actual value of y for each individual observation, squaring that and taking the sum. And this is the unexplained variation in y. It's also equal to the total sum of squares, SST, minus the regression sum of squares, SSR. And this is the variation in y not explained by our regression line, also known as the residual. Okay, so what we're often interested in is the overall fit of our regression. And so this is also the amount of variation in our dependent variable y explained by the regression line. And the measure that we use to measure that overall fit is the coefficient of determination, r squared, which you've also seen in Module 10. And so this is a measure of how much of the total variation in the dependent variable y is explained by our regression line. In other words, what percent of the total variation in y can be accounted for by the regression line that uses x to explain y, or how much of the dependent variable is explained by the independent variable. And so r squared, you can see the formula down below there, that is equal to the sum of squared distances of the actual y's from the regression line divided by the sum of squared distances of the actual y's from the mean of y, which is also the explained variance divided by the total variance, which is also the regression sum of squares, SSR, divided by the total sum of squares, SST. And you can see the formula for that there. And so this R squared is always strictly positive and ranges from 0 to 1. The closer to 1, the better the fit of our regression, the more of the total variance that we've explained with the regression. So an R squared of like 0.9, that means we've explained 90% of the total variance in the dependent variable with our regression. So that would be a very good R squared. In healthcare, you almost never see an R squared that good unless we're looking at like the variable that we saw in the first lecture that's very closely, where the two dependent and independent variables are very closely tied together, such as charges and length of stay. Okay, so there are two different kinds of hypothesis tests that you can do with linear regression models. The first kind is of the overall fit of the entire regression model using the F statistic. And this is just testing whether the regression line is a better fit than the mean. In other words, does it improve on just using the mean of the dependent variable for prediction? And so you use the overall F statistic for the regression. And what we want to do is reject the null hypothesis that the regression is no better than the mean of the dependent variable. Formally, this is a test of the null hypothesis that x and y are independent. And so we're going to use an F statistic, and we want the F statistic to be greater than the critical value of F to reject the null. And we talked about the F statistic a few modules ago when we discussed ANOVA. And so if you'll recall, the critical value of the F statistic is found using the alpha value, typically 0.05, and then two different numbers for degrees of freedom that you look up and coordinate on the F table. V1, when we're doing a simple linear regression, is always equal to 1. V2, the second component of the degrees of freedom, is equal to n minus 2. In other words, the number of observations minus 2. And so the F statistic is the mean squared of the regression divided by the mean squared error, which is, if you have this regression sum of squares and the error sum of squares, you can see there how you calculate it. SSR divided by 1 in the numerator, and then SSE divided by n minus 2 in the denominator. And that's how you get your F statistic. So the key is having calculated your regression sum of squares and your error sum of squares. The F statistic is just a ratio of those two. Okay, so there's another there's another hypothesis test that we use in regression models. And so this is where we're testing each individual regression coefficient. And so we're using the T statistic. Now in our case, we're doing simple linear regression, so we only had one variable x, regression coefficient. And so what we want to test is whether our individual regression coefficient, the slope on that independent variable, which is referred to as beta 1, we want to test whether that is statistically significantly different from 0. Right? If it's not, then it means variable x doesn't have any influence on variable y. So the null hypothesis is that x has no influence on y. In other words, that beta 1 equals 0. Beta 1, it follows a t-distribution, right? Because of the assumptions in linear regression, beta 1 always follows a t-distribution, so we use the t statistic. And so you've probably had you have had a lot of experience now based on our assignments using the t-distribution. And so the steps of hypothesis testing here are, first of all, you want to set up your null hypothesis that beta 1 equals 0. Secondly, you set up your alternate hypothesis, which is that beta 1 does not equal to 0. In other words, x has a significant influence on y. Thirdly, you choose your desired alpha value, typically alpha equals to 0.05. Whether your test is one or two-tailed, in this case it's two-tailed, and you also want to identify your sample size n. Your degrees of freedom are equal to n minus 2, and then you also want to identify the critical value of the t-score for the rejection of the null hypothesis, and you would do that using the table in your book just like you did in your last homework assignment. So to compute the t-statistic, in this case, the t-statistic is equal to the actual value of the regression coefficient beta 1 divided by the standard error of beta 1. And so you can see that number 5 down below. And so the standard error of beta 1, so you've already calculated beta 1 at this point. The standard error of beta 1 is kind of complicated. It's that formula there, right? The square root of all that complicated looking stuff. Well, the good news is the numerator in that, inside that square root sign is the mean squared error, which on the previous slide you calculated. If you have the sum, the error sum of squares, SSE, you divide that by n minus 2, that gives you your mean squared error, and that's actually what's in the numerator there under the square root sign. And then in the denominator, that's simply the sum of squares of your x variable, your independent variable. You take the square root of that, and you have the standard error for beta 1. And so once you have that, then you calculate the t-statistic. Depending on what it is, you decide whether to reject or fail to reject the null hypothesis. So let's go back to our example here, looking at the relationship between hospital charges as our dependent variable y and length of stay in days as our independent variable x. You can see in the table there the 20 patient observations plotted that I previously showed you and the statistics that I previously showed you. And so now let's calculate using the same table, r squared, f statistic, and the t statistic. So first let's start with r squared. So r squared is equal to the regression sum of squares divided by the total sum of squares. So previously we had already calculated y minus y hat in the table. And so y minus, now what we would want to do is square y minus y hat. And so that, if you look at that big table there, is the last column on the far right hand side. You then take the sum of that and you get the total sum of squares, which if you see on the far right of the slide, the table there where it says SST, that is equal to the sum, SST, let's make sure I got this right. SST is equal to y minus y bar squared. SSR is equal to y hat minus y bar squared, and SSE, okay, that's where I was going with the y minus y hat. So basically you're taking, to calculate the total sum of squares, regression sum of squares, and error sum of squares, you're squaring variables that we've previously calculated for the regression. So we previously calculated y minus y hat. You square it in that far right column and then take the sum of it to get SSE. We also want to calculate y hat, which remember is our predicted value of y. So if you look, it's kind of in that middle column of the table there, the predicted y hat. If you subtract the mean from that, so y hat minus y bar, and then square it, that's in the second last column of that big table there. So you subtract the mean, you're just subtracting the mean of y, that's what y bar is, from your predicted value of y, which is y hat, squaring it and then summing it to get the regression sum of squares, which is the numerator of r squared. The denominator of r squared on the top is the total sum of squares, which is equal to y minus the mean squared, which you previously calculated. But here you're just taking the square of y minus y bar, which is in the third last column, and summing that up. So as you can see, those are big numbers. This total sum of squares is 78,992,756. Regression sum of squares a little over 61 million. So we're getting an r squared of 0.78, which means the regression is a pretty good fit. We're 78% of the variation in our dependent variable y is explained by our regression. So the f statistic, once you have calculated the regression sum of squares, total sum of squares, and the error sum of squares, it's pretty simple, right? F statistic is the MSR, which is equal to our regression sum of squares divided by 1. So it's the same thing as our regression sum of squares, a little over 61 million, divided by the numerator, which is our error sum of squares, which we calculated as the total sum of y minus y hat squared. And so that comes out to, you can see there, SSE, it comes out to a little over 17 million. You're dividing that by n minus 2 to get, it looks like 972,458. And so the F statistic then is simply that MSR divided by the MSE, and you get an F statistic of 63, which is, so that's 61 million divided by 972 some thousand. 63 is quite large, so much larger than our. Anytime you get an F statistic that big, you're always going to reject the null hypothesis, and so here we would reject the null hypothesis and conclude our regression model is a much better fit than just the mean of the dependent variable. Lastly, computing the t-statistic. And so remember, the t-statistic is simply our beta 1 regression coefficient that we previously calculated of $806.43 that goes in the numerator, divided by the standard error of beta 1, which is equal to 101.4. So we get a t-statistic of 7.95, but you're probably here what you're interested in calculating is the standard error of beta 1. So it's the square root of the mean squared error, which we've already calculated, right? That's the error sum of squares, SSE, divided by n minus 2. So that you plug your mean squared error into the numerator there in the equation for the standard error of beta 1. And then in the denominator, you're plugging in the sum of squares of x, right? Where you're subtracting the mean value of x from each value, squaring it, and taking the sum. And remember, you already had to calculate that up in that little table to get your beta 1 regression coefficient. And so you plug those values in, and what you end up getting for the standard error of beta is 101.4. And so that goes into the denominator of the t-statistic, and you get a t-statistic of 7.95, which is quite large. And so once again, we're going to reject the null hypothesis, meaning that we're rejecting the null hypothesis that our variable y and variable x are independent, and we're concluding that x has a significant influence on y. And so next I'm going to walk you through in Excel how to actually calculate these.